Okay, so now we're back for our next video. We're going to finish up this section on section 2 of the water class. So, moving back into our slides, we left off kind of covering this figure, and as you've probably experienced in drafting your lab report, you can actually figure out what these numbers mean with respect to this index. So if you have a number of like 85 parts per billion, well, we didn't do chlorophyll A, but say we had a number of 130 parts per billion total phosphorus, or 300 parts per billion total phosphorus, what would that equal on the trophic state index scale? So obviously, if you're up here past 150, then you're going to be past, kind of up. If you're, 300, you're probably up more like 90 or something like that on this hypereutrophic scale. So you might be off this scale that we see here. So there's a mathematical relationship between this and these numbers. So Carlson's provided those formulas in his paper, and there are several formulas available online. So maybe I'll just pause this video and show you how you can view those formulas. All right, so I've pulled up this website from the North American Lake Management Society that also goes by NALMS. And on their website, they provide these formulas. And I've provided you the links to this information already in Blackboard before on writing your lab report for your use, or I've definitely provided you some information on that. So Secchi depth, it's a 60 minus 14.41 times the natural log of the Secchi depth. However, it's important to pay attention to the units, and they don't necessarily show them right there. So you have to look down here, Secchi depth units, meters. All right, so if I provided something in centimeters or inches, you need to convert it to meters. Phosphorus, the units for phosphorus are in micrograms per liter, parts per billion. That is not milligrams per liter. If you record it, which the instrument provided, the spec provides milligrams per liter, it's really important to switch it to micrograms per liter. It's very important, like if you were in a different profession, like nursing, you screw up micrograms and milligrams or cc's with something else in terms of units, somebody gets killed. So units matter a lot. So the difference between micrograms per liter and milligrams per liter, is 1,000-fold, 1,000 times difference. So you need to do this formula to get the trophic state index for total phosphorus. 14.42 times the natural log of that total phosphorus value in micrograms per liter plus 4.15. Order of mathematical operations matters a lot, so you probably want to figure this number out before you try to plug it into the formula. So figure out somewhere else the natural log of your total phosphorus value, get that number, then multiply that number times 14.42, then add 4.15 to that, and that will give you the TSI value. And that TSI value very well may be larger than what you've got on that table. And these data actually come from Carlson's trophic state index paper. So they actually, I think, cite it down here. Let's see, Carlson, 1977, trophic state index for lakes. And I will paste that in there, and we will pull up the article. Here it is. I'm not even on the EKU campus, and the PDF is available. It's been cited almost 5,000 times. And here's the actual paper. And here are where those formulas come from. Those formulas did not come from that website. They were simplified in that website for you to see, but those formulas that are on that website come from right here. So instead of citing the website, if you're putting this in your paper, you should be citing Carlson, 1977, a trophic state index for lakes. It was published in the journal Limnology and Oceanography. So that's where the formula came from this peer-reviewed paper, not from the website, even though the website was heavily influenced by this paper. This is what you would cite. All right, back to the video. So again, if you have any questions, you can definitely reach out to me, email me, call me, text me, particularly if you're having issues with writing your lab reports. Again, those lab reports should be a team effort. Review each other's work so that it flows together. All right, now I'm going to get back to the notes for things that are most related to your exam. So how do we control eutrophication? Remember, we called this anthropogenic eutrophication. We can also call it cultural eutrophication. So we can use BMPs. What are BMPs? Those are best management practices. So we can slow the rate of runoff off of our fields. We can slow the rate of runoff off of like the surfaces by not having as many impervious or paved over surfaces. Some of these farm fields, they have, if you remember from the one video I showed you on Lake Erie, or not Lake Erie, but on Grand Lake St. Mary's, the farmers showed the pictures of the clay tiles underneath the field, and they can turn on and off where those things flow to prevent the runoff. Those fields are wet sometimes, so they put pipe underneath of it to help drain them in wet areas. And you can control how fast that drains off those fields if you put in these tile stops that stop the flow of water through these underground kind of pipe systems that were laid. And that can slow the volume running off into our fields. We definitely shouldn't just be land applying manure just because we've got nowhere to put it. So land applying or over applying fertilizer when the fields don't need it is a problem. So if the soil doesn't need it, then don't keep applying it. And then don't do it when the ground's frozen, because you know that there's going to be way more on the surface, and when the ground thaws out and the spring rains come, if you're applying manure when it rains and the grounds thaw out, all that's going to run right into the water well before the growing season has even started. We can't have our big cities engaged in this practice of having CSOs and SSOs. So the US EPA is trying to reduce those. You should be familiar or remember those acronyms: combined sewer overflows and sanitary sewer overflows. And then lastly, we don't want our wastewater runoff going into like lakes. It's better to make sure that our wastewater plants are situated along flowing water bodies. We talked about Lake Washington being a problem, and there are a few other examples, but that's kind of the main points there. Now, our lakes sometimes in the summer, and this is kind of getting at turnover, and we've already covered turnover a little bit in here, but there are 3 different zones of lakes, and these zones are more profound or common in eutrophic lakes, the nutrient-rich lakes. So we know that in our most nutrient-rich lakes, we get this stratification that may occur. So we're going to do a video here on lake stratification. I think I'm going to do this in the next video, where we kind of cover the epilimnion, metalimnion, and hypolimnion, and how they kind of are set up, and how lakes mix, and how we can have these inversions that happen where the water is mixed and the stuff on the bottom is resuspended. and how that can present problems for water quality, for drinking water plants, as well as cause algae blooms. So I'm going to do that in the next video. So I'm going to stop this one here, and we'll carry on here shortly.